Okay, hello everyone. Welcome to Lecture 17. We have two topics today. We're at the end of chapter 2 of our curriculum content. So it's a good time maybe to pause, take a little pause and just have a chat about the exam that's coming up at the end of the semester during the summer exam session. So I know you didn't have an exam in the first semester due to everything that was happening. So this is probably your first experience for most people of a formal exam session here. So let me just say a few words about the sort of general context, what to expect in the semester 2 paper. So first of all, it's a 2-hour paper. It'll be managed remotely, so everybody will be at home working on it, and the submission will be via Blackboard. And we'll talk later in more detail about sort of the exact protocols for that and the mechanisms for it. But I guess the short thing to say about it is, don't worry, it'll be all right. We'll be available throughout for contact, and if there are any issues about connectivity or anything like that, we'll figure them out. Okay, usually, so far so good. We have some experience now with managing exams like this, and so far they've generally gone all right. I mean, it's not an ideal situation, obviously, but it is manageable. Okay, so about the paper itself then. So I can only really comment on the calculus part because that's my part, and I'm sure that Dane will comment on the algebra part, but basic setup will be similar to recent years in terms of the format, style, and general content. I guess the one big difference is that something that hasn't happened in other years is that you will have your lecture notes available to you. It's an open book exam in that sense. So, you'll have access to lecture notes, the general curriculum content, things like that, which I think is a good thing because that's how we do mathematics. We don't do it in a vacuum. We do it with access to our resources. So it's more authentic maybe in that sense. On the other hand, time is short. There'll be 2 hours and essentially 6 questions to answer across the calculus and algebra sections. So on the calculus side, there'll be 3 questions, one based on each chapter of the lecture notes. So basically sort of the structure of the course, the way it's been organized, will be sort of mirrored in the exam. And in that sense, I hope there won't be any bad surprises. The first of the 3 calculus questions will be about the first chapter of our lecture notes, second and third about the second and third chapters of our lecture notes. And I suppose the kind of format and style of the questions is also reflected in the homework sheets. So as you know, the first 2 homework sheets were based on the first chapter in calculus, the second 2 homework sheets on the second chapter, and the last 2 homework sheets will be based on chapter 3, which is still remaining ahead of us. So that's the way the structure is. Something that is, and the other thing I suppose I'll remark is that if you have a look back over the last few years of exam papers, maybe, I'm not suggesting that you should rely overly on old exam papers, but it is useful to get a sense of the format and style of questions that people are inclined to ask. I've taught this section of calculus quite a few times in the last 10 years, not every year, but at least sort of 7 or 8 times of the last 10. And so, when you look back at the old exam papers, you'll see the person's name at the top of them, who was the lecturer in that year. So I suppose this year it'll be me, so you can notice the ones that were mine in the past as well, which is something that's worth noting, maybe, if you're just to get a familiarity with the typical style. Okay, not that they're that different in other years, but different people have a slightly different way of asking questions sometimes. So, okay, that's the main comment. And I guess if anyone hasn't looked at previous old exam papers before, they are available through the ISS website. So just Google old exam papers NUI Galway, and you'll easily find the search environment for them. Okay, back to the content and format. So something that's similar to the 2019 paper, but not necessarily to every year before that, is that each of the 3 calculus questions will have 4 parts, A, B, C, and D. And just sort of, I suppose, for convenience for myself and for you, the 4 parts have equal weight. So the way I usually manage it is that each question carries 20 marks, and each of the 4 parts, A, B, C, and D, will be worth 5 marks each. So it's sort of, I guess it gives us all a little bit of context to know how what we're doing weighs into the total. And so that's how it goes. So there'll be 6 questions in total, 3 calculus and 3 algebra. So I suppose you could say that each calculus part is 1/6 of each calculus question is 1/6 of the exam. So each part of that is 1/24 of the whole exam. For full marks, you have to answer all the questions. Okay, so I guess in terms of what sort of ingredients might be in the 4 questions, the 4 parts of the questions, if you have a look back again at my old papers, the 2019 is the most recent one that was mine, last year's wasn't. You'll kind of see there's this kind of mixture of things. I might ask you for an example of something with some property, an example of a set of real numbers with some property. I might ask you for a definition or a statement of something. This year, I guess it's a tiny bit different in that it is an open book exam this year, which is different from other years. So you might see the occasional part, not very many, old papers that ask for something like a definition that, you just have to basically look up in the lecture notes. So I guess there never was very much of that. There'll be less this year of things that can be answered by transcribing directly from the lecture notes, because everyone has the lecture notes with them, which is unusual this year. So I probably won't ask very many questions like, give the definition of this, because it doesn't really make sense to me. But anyway, there never were too many of them. So I suppose what I was thinking of, since we've just finished with chapter 2, and that's in everyone's mind recently, was just to have a look at maybe a typical kind of question 2 based on chapter 2 of the lecture notes. So I have an example here, and actually it's the example from the 2019 paper, which just makes up the rest of these couple of slides. And what I was thinking of was, rather than me giving a kind of a prepared answer to it, was that we could try to kind of work through it, kind of imagining that we were in a sort of exam type situation where you're working on the fly and you don't have time to sort of go back over everything, and you're just trying to give an answer that conveys to the person reading it, which will be me, that you understand what you're doing. What else was I going to say? No, it'll come back to me. Okay, so here's the 2019 question 2 of the calculus section. We will have a look back at the end as well at question 1 and question 3. Question 1 is integration. So basically the 4 parts there would be some sort of integration tasks to do. Questions chapter 3 we haven't looked at yet, but chapter 2 is the stuff about real numbers and sets of the real numbers. And so I suppose within chapter 2 we had quite a lot of concepts. We had the concept of cardinality for finite and infinite sets. We had the idea of infinite sets having the same or different cardinalities. We had the concept of countability. And then yesterday we had the axiom of completeness and the idea of the supremum and infimum of a bounded set, which may or may not have a maximum and minimum elements. So those are the sort of themes that we had in chapter 2, and they will be spread over the 4 parts of the question. So last year, or not last year, 2019, here was the first part, part A, which was worth 1/4 of the marks for question 2. And so basically we were asked to look at these different finite subsets of the real numbers and give their cardinalities. So this is a question that had 5 marks attached to it, 1 for each of the 5 parts. And I suppose, I think these are questions which are, I don't know, I mean, if you see what to do immediately, they're probably not so bad, but they're also kind of, they're pitfalls that you can easily get stuck in. So let me just sort of say how I would go about this. And maybe having the lecture notes available to you is a help this year, but also bear in mind that you won't have time to be sort of looking up everything. You need to be familiar with the notation. So I suppose I'd say this is a question that people generally answer quite well, as far as I recall. The things I suppose that could throw you on a question like this would be if you just didn't recognize the notation, or if you weren't sure what you were being asked for. For example, what's the difference between part 1 and part 2 here? And maybe the last couple of parts require a little bit of sort of general knowledge that isn't necessarily just about the content of chapter 2. So let's see what we would say. Okay, so in the first part, we're asked, and so actually, yeah, let me try to indicate as well what I would think of would be sufficient as a written answer, as well as sort of saying what the answer to the question is. So if we were working on this, part 1, we're asked, what is the cardinality of the intersection of z, the set of integers, with the closed interval 1, 3 of the real number line? So the answer is 3. Okay, so if you're thinking the answer is 3 and you write down the answer 3, that's an absolutely perfect answer to the question. That is completely sufficient, and it would get the mark, which is 1 of the 5 going for that part. If you were in any doubt at all, or if you were kind of puzzled about what exactly you're being asked for, I mean, the note here is that the closed interval 1, 3 is a set of all real numbers between 1 and 3, including the endpoints 1 and 3 themselves. So we're asked for the intersection of z, the set of integers, with that closed interval. So, if you're unsure about the notation z there, about the intersection notation, just sort of try to look back at a few questions like this and remind yourself in advance. So we're asked which integers belong to the set 1, 3. So if you're wondering about that, well, we've got 1, we've got 3. We're talking about all the integers in the range 1 to 3, including 1 and 3 themselves. There's another one in there, which is 2. So this set is just 1, 2, 3. And its cardinality then is 3. So the cardinality of z intersect closed interval 1, 3, which you could write with vertical lines around it, as you know, is 3. So basically you're being asked, how many integers are in the open interval 1, 3? That's the question. The answer is 3. Okay. So I suppose as an examiner, the comment I'd make is, my job as an examiner is to try to assess how well you've achieved the learning outcomes for the course, which should be a focus for all of us as we work on it. Your job as a student taking the exam, I suppose, is to persuade me that you have achieved the learning outcomes. And it's a very imperfect system of communication in that respect, because, you know, the way it works is I make up some questions and ask you to answer them at a specified time interval, on whatever date it is. You write something and that comes back to me, and I read it, and you know, there's no opportunity for us to communicate directly. So I have to try to do my best to figure out from what you've written whether you've achieved the learning outcomes. And so I guess my comment to you there would be, you know, make sure that what you write gives me the best chance to see that you've achieved the learning outcomes. So like if you're certain that the answer is 3 and you write 3, that's absolutely fine. I'm confident that you know what you were doing. If you're anyway unsure about what the answer is and you just write an answer, so let's say you accidentally write 2 or something, then I have really no idea whether you, what you were thinking when you wrote that. So if you're, you know, if you write something like this, I can see that you were thinking about which integers belong to that interval. Even if you miss one of them or whatever, I can sort of see what you were doing. So I suppose I'm not saying that you should write a lot, but I'm saying that, you know, I'll be reading what you've written with the intention of trying to sort of identify that you have achieved the learning outcomes. And sometimes I have a better chance of doing that if you've written a little bit more. If the answer is just one word or one character, like in this case, and you're certain that your answer is right, there's really no need to do any more. But if somebody gave the answer 2, but they wrote this down, I'd see that they, you know, that they were thinking along the right lines. Okay, second part. Z intersect here, we've got the open interval 1, 3. So this does not include the elements 1 and 3 themselves. So we're asking here, which integers are in the open interval 1 and 3, 1, 3. So which integers are in the range 1 to 3, but not include, but strictly greater than 1 and strictly less than 3. So the answer here is 1. The cardinality of that set is 1, and the set, the intersection of the open interval 1, 3 with the integers consists only of the element 2. Okay, so just be a bit careful. I guess, you know, there are pitfalls here. You know, somebody could write down 2 because they could be thinking of the number 2, which is the only element of that set. The answer is 1 because the cardinality of the set is 1. There's one element there. So just kind of be attentive to the detail, that what exactly it is that you're asked for. You know, there's not a lot to write. I mean, the answer again to this question is just one character. It's just 1. So there's, you know, but there are kind of, if you're inattentive or anything, or if you kind of don't pay attention to the details, you could easily accidentally write down the wrong short answer. So just make sure, what are we asked for? We're not asked what is the element of this set. We're asked what's the cardinality of the set. That means the number of elements in it, and that number is 1. So there's one element in that set. Okay, so again, this answer by itself would be more than sufficient. Would be sufficient. Just 1. If you write something like this, or if you write that and then say, so the cardinality is 1, that's absolutely fine as well. So there's, you know, there are many different perfect answers to these things. Okay, part 3, the set of integers x for which x squared is less than or equal to 10. So again, this is not a, you know, it's not so hard to count these things, but be careful, you know, what are we asked for? We asked for, so, you know, if you're an integer and your square is less than 10, that means you're basically in the range, you know, 1, 2, 3, 0, plus or minus. So the set in question here, make sure that you include all of them, you know. 1 is an integer whose square is less than or equal to 10. 2 is another one. 3 is another one. 4 is not, because 4 squared is greater than 10. But 0 is there, don't forget that. And -1, -2, -3 are all there as well. Okay, so it would be easy to forget the negative ones or something, or to, you know. So the answer is 7 here. And the reason why it's 7 is because this is the list of integers in our set of concern. There are 7 of them. Okay, so if somebody wrote down 5 or 4, I wouldn't really know what they were thinking. You know, I'd see an answer that's not the right answer. But if they wrote down 4 maybe, and they wrote some, and they had some notes kind of like this accompanying it that sort of showed which 4 they were thinking of, maybe I'd have some sense of what they were trying to do or what they were thinking about. Okay, so 7 by itself is a perfectly good answer. If you're thinking about it, and you can, there's no harm in sort of writing a couple of rough notes even for yourself, and you know, I'll notice all those kind of things. Of course, if you can answer it without writing any rough notes, that's absolutely fine too. So part 4, the question was, what's the cardinality of the set of prime numbers that are less than 20? So here again, I guess the easy way, or the only way to do it probably is to either in your head or in writing, note the prime numbers that are less than 20. What are they? 2, 3, 5, 7, 8, 9, 10, 11 is the next one, 13, 17, 19, there are 8 of them. So the answer is 8. Okay. So, if somebody was writing a list like that and they forgot one, I'd probably let them get away with it. But if they wrote down sort of 5 as the answer, I wouldn't know what they were thinking, so it would be harder to let them get away with it. Okay, if you write down 8 as the answer and write nothing else, that's a perfect answer. Okay, and then finally, the set of solutions in R of the equation x to the 4th minus 1 equals 0. This is slightly trickier, I guess, because it requires it requires a little bit of knowledge of polynomial equation solutions. So we know that x to the 4th minus 1 is x squared minus 1 times x squared plus 1. So it's x minus 1 times x plus 1 times x squared plus 1. And so the roots of that polynomial, x to the 4th minus 1, are the roots of x minus 1, x plus 1, and x squared plus 1. And we can notice we're asked for the number of solutions in the real numbers. So, again, it would be easy here if you were kind of rushing or not being really careful to just write down the answer 4, because it's a polynomial equation of degree 4. But we're asked for the set of solutions, the number of solutions in R. So we shouldn't count ones that aren't in R. So here, the roots of x to the 4th minus 1 are either roots of x minus 1, there's one of those, 1, it's a real number. Roots of x plus 1, there's one of those, minus 1, it's a real number. But the roots of x squared plus 1 are not real numbers, they're the complex 4th roots of unity, plus and minus I. So the answer there is 2. And the set in question is the set consisting of 1 and minus 1. Those are the only real solutions of the equation x to the 4th minus 1 equals 0. Okay, so again, I suppose, if you wrote down something that wasn't the right answer as the number of solutions, and you had some accompanying even rough notes that I could glean something from, I would have a look at them. Okay, that was part A of question 2 in calculus in 2019. I'm not saying it will be the same this year exactly, but something along those lines might easily happen. Anybody have a comment or question there? Yes, so the answer there, do we have to scan? Yeah, that's exactly it. So there's a various software. The one that most people use is called Office Lens, to just sort of convert a handwritten note into a PDF file, and it works quite effectively. So I mean, I guess everybody will need a phone or some kind of camera that can do that job. And we'll talk about it later anyway, about the details and mechanisms for submitting work. You'll be probably quite used to it very quickly because it'll be happening in every subject. But yeah, that's what happens. Everyone creates a PDF from their handwritten document and uploads it to Blackboard. We practice that in advance. Okay, so that was part A, 2019. So that's 1/4 of the question answered. Part B, so this is kind of a little bit more, I suppose, onto the kind of theoretical elements of chapter 2 of our lecture notes. So again, 5 marks here. What does it mean for an infinite set to be countable? And show that the set of integers is countable, and give an example of an infinite set that is not countable. So I guess all of this is, I suppose, kind of knowledge from chapter 2, but it's all sort of serious stuff that probably requires quite a lot of work to understand well. So, so I suppose to give an answer here, what does it mean for an infinite set to be countable? And again, like, there are lots of ways of saying this, and I'm not insisting on any sort of particular form of words here. If you write something that shows me that you know what it means for an infinite set to be countable, then you'll get the marks here. So I'll write something, and I'm not saying here that this is the only form of words that would be acceptable. I'm saying that this is something that I would see as a reasonable answer. So an infinite set is countable. That's the term that we're defining. If its elements can be put in bijective correspondence. Oops, bijective correspondence. With a set of natural numbers, with the natural numbers. So that's one answer to that I would see as perfectly fine. If somebody wrote an infinite set is countable if its elements can be listed, I would accept that as well. That would be fine. If somebody sort of drew a picture of the natural numbers and some kind of arrows kind of representing the correspondence between the natural numbers 1, 2, 3, 4 and the elements of this set, and kind of explained it like that, that would be fine as well. So it doesn't have to be any sort of particular form of words, but I suppose when you're thinking about it in advance, like think about the person who'll be reading it, and will they see from what you've written that you know what it means for a set to be countable? Okay, that'll be me. Okay. Okay, so show that the set of integers is countable is the second part. So actually, I should say as well, maybe like if there's something like this, so this kind of has three parts. What does it mean for a set to be countable? Show that the set of integers is countable and give an example of an infinite set that's not countable. So, I don't really say on the paper how the 5 marks are broken up over these three elements, but basically they're sort of, the first one maybe is worth 1 and the second two each, something like that. So, there could be a level of granularity where the marking scheme isn't sort of split up to that extent, but there's 5 marks for each of this, and some proportion of that will be for each side. Okay, the set of integers is countable. So again, I mean, I don't insist on a lot of writing because I know that you're under time constraints. So you could say something like a bijective correspondence between Z and N is given by this table. So let's say we have a table, or if you call this a table, I don't know, where we have natural numbers on one side and integers on the other. It's kind of a table with 2 columns, I suppose. So we got a 1, 2, 3, 4 in the natural numbers, and so on. We could put some dots to indicate that this continues, and we have to sort of give enough information to show that we've got a correspondence between the integers and the natural numbers that will sort of continue and pick up all the integers. So usually people start with 0, and then maybe go 1, -1, 2, -2, and so on. So I guess in my opinion, that would sort of be enough of a start to indicate how it goes. If you want to, it's probably useful to put a little arrow or something to indicate that 0 matches the 1 and -1 the 3 and so on. 2, 4, -2, 5. If you want to write down a formula that tells you what the integer is that corresponds to a given natural number n for the evens and odds, that's also absolutely fine, and I guess in some ways kind of more rigorous, but either is fine for the purposes of this exam. If you want to kind of draw, if somebody might decide that they'd like to draw this, the picture with the kind of arrow that runs through all the integers and explains how this correspondence goes, which here are the integers 0, 1, 2, 3, and so on, -1, -2. So if somebody decided that they were going to kind of give this picture to indicate that we start at 0, then we go to 1, then to -1, then to 2, then back to -2, and so on. That would be also fine. I think by itself, if it's arguable whether it would be a complete answer. So if you're going to sort of use a picture like that to explain it, probably useful to also write kind of a little note saying, the arrows here kind of indicate how the integers can be organized into a list or something like that, or maybe give a little bit of this kind of table as well. Okay, so certainly, I mean, what's written there, if somebody wrote exactly what I've just written here, which I'm not claiming that it's a beautifully presented or thing or anything like that, but it would get full marks for me in this exam. What is for that part? Okay, and then thirdly, an infinite set that's not countable, an uncountable, an example of an uncountable. I suppose I should write. I should probably try to write some kind of correct sentences. An example of an uncountable set is, for instance, the full set of real numbers would be an example, or so is any open interval. So for example, most people's favorite example is the open interval 0, 1, because that's the one that's usually used for presenting cantors diagonal argument. So that, I mean, if you just wrote 0, 1 without any words around it, I'd give you full marks for that as well, because of the time constraints. But it's probably better to write in sentences if we can. Generally, it's a good habit. So okay, so that answers that part B. Okay, and that's another 5 marks. So I mean, it might be that some parts take a little longer to answer than others, even though they carry the same marks. Okay, anyone have a comment or question about that? And again, like I really want to emphasize, I'm not saying that this is the only way to answer these questions. What I'm trying to do is give an indication of kind of the level of detail that I would expect. And there are many ways to say something, and people have different preferences, and that's completely fine. Okay, onward, if nobody has a question. Oh yeah, here's part C. So this part, I think, is probably a little bit trickier, and it relates to the stuff that we were talking about yesterday. The sets of real numbers that are bounded, and they're infimum and supremum. So this part, I think, is probably like a part that students that year found trickier than the first two parts. I think it is a bit tricky because we've got this set of numbers, and we've got to kind of figure out, what are the numbers in this set? What do they look like? What are they, what is it that we try to find out about them? So what we're asked for is to determine the infimum and supremum of this set. Okay, so from the fact that we're asked for that, we can kind of probably take it that the set is bounded, but that's maybe not even obvious from the way that it's presented. And then we are also asked, does S have a maximum and or a minimum element? Okay, so I suppose, the infimum and supremum, as we saw yesterday, are kind of technical definitions. The infimum is the greatest lower bound, and the supremum is the least upper bound. So there's this kind of like technical machinery that goes with that, and these sort of formal definitions. We're also asked, does S have a maximum or a minimum element? And I think something that's tricky for most people, certainly for me, is to kind of move from these kind of technical definitions to, okay, here's a set S, do something with it. So I suppose, even though it's important to have the precise definitions in our mind and be able to work with them and deduce with them and, engage in reasoning with them, it's also important to be able to kind of interact with things at a practical level. So, if we're asked about the infimum and supremum of the set S, what we're basically asked about is how small can elements of the set S be, and how great can they be? What are the biggest elements in S, and what are the least elements in S? So I think if I was kind of trying to tackle something like this, that would be the first question I'd have in my mind. What are the biggest elements in S? What are the greatest elements? What are the least elements? Where are they? And then worry later about whether it's a supremum or a maximum, or whether the set actually has a maximum and a minimum element. So we have to get our hands on what are these elements of S. So here I'm going to write something that, I'm not saying would be sort of that I'd write in an exam answer, but I'm saying this is what would be going through my mind if I was tackling this question. So, what are the elements of S? And, and then I suppose to kind of get into the question of what the infimum and supremum might be, we have to ask what are the greatest elements? Where are the kind of low upper bounds? Okay, this is not a very precise thing to write. So I mean this as a kind of point to think about rather than a precise, something that has a precise meaning when you write it down. Okay, so elements of S are rational numbers of the form n squared minus 2n over n squared plus 1, where n is an integer. Okay, and I suppose it's a little bit hard by looking at that to get a sense of, what are the elements in S. If I hand you a particular rational number, like is it an S or not? You really need to get a little bit of a sense for what this set really is. So we can observe, I suppose, that the denominator n squared plus 1, that grows when n increases. There's an n squared in the numerator as well. So a suggestion is to write a typical element of S as and again, I'm not saying that this would be sort of something that I would, that this would be sort of the complete exam answer. This might be some kind of rough workings or something like that. But noticing that we have n squared plus 1 in the denominator and we have n squared in the numerator as well, we could write the numerator as n squared plus 1. Okay, there's no 1 in the numerator, so we have to compensate for that by subtracting off that 1 that we just introduced over n squared plus 1. And an advantage of that is that that term with the n squared in it, we can just then sort of cancel with the denominator and write that's n squared plus 1 over n squared plus 1 minus 2n plus 1 over n squared plus 1, which is 1 minus 2n plus 1 over n squared plus 1. Okay, so the 1 is 1. That doesn't change for different values of n. And I guess the advantage, in my mind at least, of looking at it this way is, what are the elements of S? Well, they're 1 with something subtracted off or added on. Okay, so, and this 2n plus 1 over n squared plus 1 part, like when you look at what happens to that for different values of n, the n squared plus 1 is sort of growing faster than the 2n plus 1 as n increases. So this bit that's been subtracted off the 1 is going to 0 as n goes to infinity. And same thing as n goes to minus infinity in that case as well. The n squared plus 1 is growing faster than the 2n plus 1. Okay, so that's one observation. So, the elements of this set S, I guess they sort of differ from 1 by this little piece. Okay, that piece looks kind of like 2n over n squared, so it's a fraction. It doesn't grow without bound. Okay, and we're asked for the what happens at the extremes of S. What are the greatest and least elements? So a few examples of elements of S, I suppose we could say, if you want to. This is kind of parenthetical. So a few examples of elements of S. You know, if n is 0, for example, n could be any integer. And that's another thing. Sometimes these questions, if you look back over old papers, you'll see them. Sometimes these questions specify that n is positive or n is negative or n is greater than something, whatever. So in this case, it's any integer. So if n is 0, the element of S that corresponds to n equal to 0, put 0 in there, you get 0 over 1. So you get 0. If n is 1, you get 1 squared minus 2. So you get minus 1 over 1 squared plus 1. If n is 2, you get 4 minus 4 in the numerator. So you get 0 again. If n is 3, you get 9 minus 6, which is 3 over 9 plus 1, so 3 over 10. If n is 4, you get 4 squared minus 8, which is 8 over 4 squared plus 1, so 8 over 17, and so on. And you can sort of see how they go as n is positive. If n is negative, so for example, if n is minus 2, you get 4 plus 4, which is 8 over 17, which happens to be the same thing that you get minus 4. Okay, so you can kind of get a feel for what sort of elements these are by writing down a few of them. I mean, if that's helpful for a problem like this, I'd say do it a bit. You might get a feeling for what happens to these elements as n increases or as n decreases in the negative direction, but don't sort of rely too much on that technique of kind of writing down a few elements. If it helps you to get a sense of what's going on, great. If it doesn't, it's all right too. Okay, so what are we supposed to do? We're supposed to determine the infimum and supremum of S. Let me insert a page here. Okay, so S again is a set of n squared minus 2n. Well, let me write it in this other way. S is the set of 1 minus 2n plus 1 over n squared plus 1, where n is any integer. Okay, so if n is positive, so the corresponding element, the element of S determined by n, is less than 1, because we're subtracting something positive from 1 in that case. Because if n is positive, then 2n plus 1 over n squared plus 1 is certainly positive, and we're subtracting something from 1. So we get something that's less than 1. And I guess what we should ask ourselves is, well, what's the biggest thing that we can subtract from 1? In an element of S. To get like a least element of S. So I guess, well, if you want this thing to be as big as possible, we should sort of limit the size of the denominator, because n squared plus 1 is growing faster than n. So if we take, for example, n to be 1, then we get as an element of S 1 minus 3 over 1 squared plus 1, which is minus 1/2. Okay. If we take n to be 2, so moving in the positive direction, so we're thinking about sort of subtracting positive things from 1. If we take n to be 2, we get 1 minus, if n is 2, then 2n plus 1 is 5. N squared plus 1 is also 5, so we get 1 minus 1 equals 0. And if n is greater than 2, then, you know, this fraction is something like, if n is 3, it's 7 over 10, so it's smaller again. So the thing we're subtracting off 1 gets smaller as n increases in the positive direction. Okay, so the least value that it ever has occurs when n equals 1, and that's minus 1/2. Okay, so I suppose this is kind of hard to describe sometimes in text. But if n is, you know, so the least, I suppose we can say that the least, so so I suppose 2n plus 1 over n squared plus 1 decreases as n increases from 2, because the denominator, n squared plus 1, and the denominator just dominates, and this value decreases. So the minimum value is obtained. It's minus 1/2, and it's obtained when n equals 1. And so we could specify that this is both the, for negative values of n, we're basically sort of adding something onto 1, so we're not going to get anything smaller than that. Okay, so that's going to be the minimum element of S, and also the infimum. And then when n is negative, so if n is negative, then we're subtracting. So if n is negative, then 2n plus 1 is, if n is negative and it's an integer. So if n is negative and it's an integer, that means it's minus 1, minus 2, and so on. Then 2n minus 1 is negative also. And what we're subtracting from, and n squared plus 1 is positive, so what we're subtracting from 1 in that case in an element of S is negative. So we're subtracting something negative, so we increase the value. So corresponding elements of S are greater than 1, because we're subtracting something negative from 1. And our question is, well, okay, so the greater elements of S maybe, or the ones which are greater than 1 at least, occur for negative values of n, and we have to ask ourselves, well, how great can they be? So we want to, to get a high value of an element of S, we want to add on as much as possible onto the 1. So again, that will occur when the denominator is as small as possible. So okay, so when n is minus 1, for instance, then we've got 1, and from the 1 we're subtracting minus 2, we're subtracting 2 times minus 1 plus 1, which is minus 2 plus 1, so that's minus 1, over minus 1 squared plus 1, which is 2. So we get 1 plus 1/2, we get 3 over 2. And that's an element of S. If n is minus 2, then the denominator is already 5. So we get 1 minus, what have we got at the top? We've got 2 times minus 2 plus 1. That's minus 3 over 5. So we're only subtracting, hang on, what have I said here? Minus 2 plus 1 is minus 3 over 5. Oh yeah, okay, so this is 8 over 5, which is greater. When n is minus 3, we've got 1 minus 3, minus 6 plus 1 is minus 5 over 10, so we've got 3 over 2 again. And when n is minus 4, we've got 1 minus 7 over 4 squared plus 1, which is 17, and that is 1 plus 7 over 17, which is certainly less than 1.6, which is the greatest values that we achieve. So the highest value is achieved when n equals minus 2, which is 8 over 5. And after that, the denominator again dominates, and the thing that we're adding on just decreases. So highest value is achieved when n is minus 2, 8 over 5 is an element of S, and it's the maximum element of S. So the maximum element of S is 8 over 5. So I guess this is a question where it's kind of like, it's a bit experimental, and I guess, it's about just sort of working with a set of numbers that is defined in a very particular way. So I don't expect you to write a sort of detailed, rigorous proof about how all the other elements from then on are going to be less than the one that occurs when n equals minus 2. I mean, the point there is that the denominators, which are n squared plus 1, are increasing, and they're the sort of bit that gets added on to 1 is going to decrease as n increases in the negative direction. So the conclusion is that the maximum element of S, which is also the supremum of S, is 8 over 5. Okay, this is an example of a set which has both a maximum is bounded. It's bounded because as n increases, the n squared plus 1 term in the denominator just imposes a bound. Like the sort of fractions that are being added onto one are heading towards 0, and then increases either in the positive or negative direction. And the minimum element of S, which is the infimum of S also, the greatest lower bound occurs when is minus 1/2, and that occurs when n equals 1. Okay, so this is this example is an example of a set which does have both a maximum and a minimum element, and and when a set has both a maximum and minimum element, when a set has a maximum element, that's also its supremum, and when a set has a minimum element, that's also its infimum. So I think this example is probably the trickiest part of this question, and it's sort of just a case of getting stuck in figuring out where the extreme values in the set S are. This isn't, I suppose, really kind of a proof as such, but it does, if you wrote something like what I've written here, it would sort of show me that you know what you're doing, that you figured out what are the elements of S, what happens to them when you vary the value of n, where the greatest elements are, where the least elements are. If you look at similar examples like this, like over the last few years, you'll find that quite often there'll be an example where there's a maximum, not a minimum. So at one end, you've got a maximum element, which is the greatest value attained in the set, and maybe at the other end, the set is bounded below, but there's no least element, and in that case, there's an infimum to be identified. So I mean, we can have another look at a few questions like this in the future, but I guess what I kind of expected people to do with a question like this was to sort of get stuck in, experiment with it, figure out what are the elements of this set, how great can they be, how low can they be, and where are they? Where are the greatest higher, upper, and lower bounds? Okay, so it's tricky, and I suppose it probably takes a bit more time as well than the other parts. So if there's something like this, and you're kind of wondering about time, you always have the option of trying to leaving it to the end and coming back to it if it's taking you a bit of time. Okay, anybody have a question about that? Okay, so the last part last year was probably quicker and maybe easier as well than the third part. So again, it's about suprema and infima. So part D had 3 parts and asked us for an example of a set of real numbers that has a supremum but no infimum. Okay, so, and again, to have a supremum, a set has to be bounded above. So it can have a maximum element, in which case the maximum is the supremum, or it can have a supremum but no maximum, like an open interval. So an example of a set that would have a supremum but no infimum, for example, would be a set that's bounded above but not below. So the set of negative integers would be an example. That would be one example. If it has no infimum, it means it's not bounded below. If it has a supremum, it means it is bounded above. So basically any set that's bounded above but not below would be an answer to that. So that would be an answer there. But if you just wrote any set that's bounded above but not below, that's not an answer because it's not an example. So I want to see an explicit example. The set of negative integers would be one. Okay, the set of all real numbers up as far as some specified point like 1 would be another one. Okay, second, has a maximum and an infimum but no minimum. So to have a maximum, you have to have a greatest element, so you have to be bounded above. To have an infimum, you have to be bounded below. But to not have a minimum, you have to not have a least element, but be bounded below. So an example of this would be something like an interval that's open on the left and closed on the right. Okay, so that set, it includes all the real numbers that are greater than 0, strictly greater than 0, and less than or equal to 1. So the maximum element here is 1. The infimum is 0, which is the greatest lower bound, but there's no minimum element. And if you're anyway sort of not sure about the brackets here and about what exactly, about reading that or about being confident about what you've written, just feel completely free to just give an explanation in words. The set of real numbers that are strictly greater than 0 and less than or equal to 1 is fine, and you can write that in words if you prefer. Third example, a set of real numbers that has neither a supremum nor an infimum, but that means any set of real numbers is not bounded on either side. So an example would be the full set of real numbers itself. Another example would be the set of integers. Another example would be the set of rational numbers. Any set that's not bounded on either side, either above or below. So any set that's not bounded, that has neither an upper nor lower bound. so that's that question from 2019. I hope it's of some help to have a look at it. I suppose, in my opinion, the sort of trickiest part of it is part C, and it's, all of it's tricky because all of it involves sort of detailed knowledge. But I guess, if you find some part of it particularly tricky or challenging in an exam situation, remember you can always sort of leave that part to last, and remember that the other 3 parts also kind of contain the same amount of, get the same credit as the one you find tricky, whichever one it is. And so make sure that you give yourself the best chance of answering all the parts for your field that which match your strengths, whatever they may be, and whichever parts you might prefer. Okay, I'm going to stop the recording there and thank everyone who's joined us for the recording. We'll resume next Wednesday, with chapter 3 of our lecture notes. And so thanks everybody. Have a good weekend. We'll see you next week.